This is a video for my accelerated students where we'll be combining gas law equations with stoichiometry from earlier in the year. The goal will be to be able to calculate the volume of gas used and or produced in a chemical reaction at conditions other than standard temperature and pressure. We'll start with a quick rundown of the learning objectives of this video. We'll start with a review of gases and stoichiometry that we've already talked about this year when we do those calculations at STP or standard temperature and pressure. And then we'll talk about the use of stoichiometry with gases more specifically. We'll talk about the STP options as well as talking about the same kind of calculations but in any other conditions besides STP. Last but not least, we'll talk about something that's a little more optional. We'll talk about that mole-to-mole ratio again and how it can be used to determine the number of moles of gas, or how it can also be used to calculate the volume of gas. As I already mentioned, this is something you don't actually need to know, but it is something that makes certain calculations much, much quicker. And again, just to recap on what stoichiometry is all about, we see this picture here on the bottom right where we have 4 reactions running, generating gases, and balloons were used to capture the gas generated. As a result, in each reaction vessel, different amounts of reactant were used, and as a result, different quantities of product were actually produced. Our job with these videos will be to calculate the quantities of gases produced, just like we've done earlier in the year. To start this process, we're going to do a quick review of some of the math and calculations we've done with stoichiometry and gases earlier in the year. In this situation, we're going to calculate the volume of water formed as a gas by completely reacting 100 grams of oxygen gas with an excess amount of hydrogen gas. What I left out of this problem, a little carelessly, was the fact that this reaction is happening at standard temperature and pressure. If you want the opportunity to practice, take a minute, pause the video, try this problem on your own. If you'd rather just see the answer put together, I'll be going through that in 2 seconds. To go over an answer, we're going to set this up just like any other stoichiometry problem. We're going to start with our given value of 100.0 grams of oxygen gas. We'll put a multiplication sign in a line. Our first conversion is to go from grams of oxygen into moles of oxygen gas by using the molar mass from the periodic table. Our second conversion factor, just like always, is to use the mole-to-mole ratio. For every 1 mole of oxygen gas formed, we're going to get 2 moles of water formed. And then finally, the step that's interesting for us this time around is the fact that for every 1 mole of water that we form, that's going to take up a gaseous volume of 22.4 liters. We set this whole thing up, we do with this in our calculator, and we're going to get an answer somewhere in the vicinity of 140 liters of water formed by this chemical reaction. Again, the key step here that's related to what we're dealing with is this last one here. This allowed us in this specific situation to calculate the volume of gas formed based on how many moles we actually had. To do this calculation, we base this on the assumption, or the conversion factor, that there were 22.4 liters for every 1 mole of gas. But again, this is only true under certain conditions, and we call those conditions standard temperature and pressure. This would be a temperature of 273 degrees Kelvin, and it would be a pressure of 1 atmosphere. Now, this is not just an arbitrary made-up number. If we go back to our gas law equations, we'll use our ideal gas law equation, PV equals N times R times T. If we actually start plugging some of these numbers in here, for example, a pressure of 1 atmosphere, a volume that we'll solve for, we said this is true for 1 mole of gas. We'll put in our ideal gas law constant and a temperature of 273. If you go through the trouble here and solve for the value of V, you'll find out that V is 22.4 liters. So what we can see here is that this conversion factor that we used early in the year is simply one possible answer from our ideal gas law equation. Now, in this video, our goal here is to not just be able to do this at one particular temperature and one particular pressure, but be able to do this at any particular temperature and pressure. And that's where we're going to come back to our ideal gas law equation. This is going to allow us to relate a certain number of moles of gas, which relates to stoichiometry, to a certain volume of gas, to a certain pressure of gas, or to a certain temperature of our gas, as long as we know all the other variables. So we're going to use the mole stuff from stoichiometry and link it to gas laws with the ideal gas law equation and the variable n. So let's talk a little bit about that process in more detail. Again, our key equation here is going to be PV equals nRT. We're going to use pressure, volume, and temperature data to determine the number of moles of gas, or the number of moles of our reactant. We're going to use the mole value in our stoichiometry calculation. Again, we're talking here about this value of n. We're going to plug into our stoichiometry. And then finally, we're going to be able to calculate the property of the product using the moles from stoichiometry and plugging all of that back into PV equals nRT. So if we're interested in how the volume of our product, the pressure of our product, the temperature of our product, etc., we get n from stoichiometry, we plug in the rest of our variables, and we can solve. Let's put this into action a little bit. Here we got our first example problem. If I completely react 2.0 liters of C2H4, which is ethene, in a tank pressurized to 2 atmospheres at 15 degrees Celsius in the following reaction, how many grams of water will be formed in the process? My plan is to go through this problem together. If you want to take a stab at this on your own, feel free to pause the video and give it a try. There are a couple more examples here in the video, though, for you to get that opportunity. So we're given information in terms of volumes, pressures, and temperatures. That tells me that this problem is going to start with our gas law equation, PV equals N times R times T. If we can get a value here for N, we can use that in stoichiometry later on. Well, our pressure is 2 atmospheres. Our volume is 2 liters. That's going to be equal to N times our gas law constant, which is 0.08206. And our temperature in this case was 15 degrees Celsius, which we can convert into Kelvin by adding 273, which is going to become to 288 Kelvin. Take a moment with your calculator. We can do some quick math and figure out what our value of N is. What we determine then is that N is equal to 0.169 moles of C2H4. And this is the number or the quantity of that C2H4 we start our reaction with. Knowing this number then, we can start our stoichiometry problem, which is going to predict for us how many moles, or how many grams in this case, of water will be formed. So we'll start with our 0.169 moles of C2H4. Because we're in moles, we can dive right into the mole-to-mole ratio. For every 1 mole of C2H4, we're going to form 2 moles of H2O. That's our key stoichiometry step. And then finally, the problem wants the answer to be in grams of water. So we're going to say for every 1 mole of H2O, there's somewhere in the vicinity of 18 grams. You can use your periodic table and get a couple more significant digits there. Once again, we're at a place where we can use our calculator. And a couple quick button pushes, and I find out that my answer is 6.084 grams of water formed by reacting this ethane gas with these characteristics above. Again, these characteristics we plugged into PV equals nRT to get moles, and then moles we plugged into a normal stoichiometry problem and ultimately to figure out the number of grams of water formed in our reaction. Just to be careful, we should round this to the correct number of significant digits, and with that information, I get the number 6.1 grams of H2O. And that's our answer. What I want you to notice before we move on is we really haven't done anything new here. We just used our new content, which is ideal gas laws, and our old content, which is stoichiometry, and simply used them together to do a new job. Here's a second example. I actually encourage you to pause the video and give this example a try on your own. In this situation, we have carbon dioxide in a 2.0 liter tank at 35 degrees Celsius. We are given 100 grams of calcium carbonate, and we're asked how much product is formed. In this situation, I would start with the calcium carbonate, figure out how many moles of carbon dioxide are made in the reaction, and then use this data and PV equals nRT to calculate the pressure of that carbon dioxide in the tank. By the way, I know we don't see any coefficients here. This reaction is already balanced and ready to go. Again, pause the video, give this problem a try. We'll go over the answer in a minute. So let's go over an answer for this one. Again, we are given the starting information of 100.0 grams of calcium carbonate, CaCO3. Our first order of business, as in any stoichiometry problem, is to convert from grams of calcium carbonate into moles. We'll use our periodic table, and we'll get a mass for calcium carbonate of approximately 100.1 grams for every 1 mole of CaCO3. Our next conversion factor then will be to use the mole-to-mole ratio. For every 1 mole of CaCO3, we're going to form 1 mole of carbon dioxide. Now, normally we'd have other steps to do, but PV equals nRT is going to use moles, and that's the unit we want to stick with. So we're going to stop our conversion here. We'll put this into our calculator, and I think we're going to get an answer very, very close to 1. We're going to get 0.999 moles of carbon dioxide formed. So that's the number of moles, but in this question we want to ask the pressure that this gas will exert in the certain tank. Well, that's where we're going to take this answer and use our ideal gas law equation, PV equals N times R times T. We want to solve for P. We're told the tank has a volume of 20 liters. That's going to be equal to the number of moles of gas in the tank, which we just determined to be 0.999, times the gas law constant, which is 0.08206, times the temperature in the tank, which is 35. We add that to 273 to get the temperature in Kelvin, and we find out the tank is at a temperature of 308 Kelvin. Again, some very quick algebra here to solve for our variable of P. And we find out that the pressure in our tank is 1.26 atmospheres. Looking back on our problem, we have 3 significant digits in a couple places. We've got 3 significant digits down here. This is going to be our final answer. So our pressure in our tank would be 1.26 atmospheres as a result of what happened in this chemical reaction. Again, it's important to note we didn't do anything new. We did a little stoichiometry here to figure out how many moles were produced, and then we plugged those moles in for N with PV equals nRT to calculate the pressure in the tank. To wrap things up today, we're going to talk about a little shortcut that you can be using in gas law scenarios like this that'll save you a lot of mathematical steps. If you don't get what I'm about to talk about, you can do things exactly the same way that we've already done. If you do get this, as I said, it can save you a little bit of time. So in stoichiometry, we use the mole-to-mole ratio to convert between amounts of one chemical to the amount of another. And that's the thing that makes special for stoichiometry in particular. With gases, and here's where we start to get into some good information here, moles of gas, and this should be R, A-R-E, moles of gas are directly proportional to the volume of a gas, meaning as the moles of gas change, the volume of the gas changes the same way, but this is under the assumption that we're at constant pressure and constant temperature. That mole-to-mole ratio then from our balanced chemical reaction can be used to do conversions for us. As we already know, it can convert us between moles of gases in the reactants and the products. That's what it's intended to do. But based on what we just said, we can also use this mole-to-mole ratio to convert between volumes of gases in the reactants and products. Because moles and volumes are directly proportional one to another, the mole-to-mole ratio converts between both of them accurately and correctly. What this does for us is it prevents us from having to get all the way into moles first. If you're given volume data in your problem, you can use that volume data to convert directly. The only catch again though, and this is the key part here, this is only true when you have the same pressure and temperature. The pressure and temperature before the reaction and after the reaction has to remain the same. If that's the case, you're ready to rock. To wrap this up, we'll talk about one example of a problem like this that it deals with this little shortcut. The question we would ask then is what volume of water vapor can be formed by completely reacting 20 liters of oxygen gas with excess hydrogen gas in the following reaction. Now we could go through all the trouble of figuring out how many moles of oxygen gas this is, use the mole-to-mole ratio, and then convert back into volumes of the other one. That would involve many stoichiometry steps, many PV equals nRT steps. Instead, we can skip right to the end game here and say that for every 20.0 liters of oxygen gas, we can say that for every 1 liter of oxygen gas, we're going to create 2 liters of water, and that's going to get us the answer we're looking for. That 1 and that 2 came from the balanced chemical reaction, just like a mole-to-mole ratio does. We can do our math here and we'll find out that we will create 40.0 liters of water vapor as a result of this chemical reaction. Notice how much quicker and simpler that is than the other steps that we've done, but again, this only works if the pressure and temperature remains constant throughout the problem. So that's it for our video. Just to recap the things that we've done, we've used the properties of gases with stoichiometry to calculate amount of gaseous products and reactants in our chemical reactions. We already earlier in the year knew how to do this at STP with the conversion factor 22.4 liters is equal to 1 mole, and you are still welcome to use that if it's an STP problem. We now today have talked about how to do that at other pressures, volumes, and temperature by using the ideal gas law equation and taking that data and using it to solve for a value of n. That n can then be plugged into stoichiometry, and then it can be used to calculate just like normal. We've also talked about the fact that that mole-to-mole ratio can be used to do a couple things now as opposed to what we used to do with it. We can definitely still convert between moles of reactants and products, but now we can also use it to convert between volumes of gaseous reactants and products. Again, this is not a key step that you need to do, but it is certainly a step that saves lots of time and effort if you understand how it works.